If we go back to introductory calculus, you might remember that if we have some function y is a function of x, then we might think about this idea of a differential, dy. And we can think of dy being equal to f prime at x times dx, where x is a differential value in x. What does that mean? Well, what that means is that if I can think about this idea of a change in y, the relationship of the change in y to the change in x, what we might think of as a slope, we say that that is the change in y over the change in x is approximately equal to that derivative. And while that's true from a limit standpoint, what it's more so saying is that if I have some fixed value xy, I can approximate the value here by using this type of function and saying that the change in y is approximately the value of that slope times the change in x. And what you find is that that's pretty true early on, but as the function goes along, that approximation becomes decreasingly effective. Now, in the case of a linear function, it's always true, but in general, functions may be approximated in small steps, but they lose the ability. That approximation falls off pretty quickly as the step gets too far out. So we do this because we want to take this idea of being able to approximate the change of a function using the derivative. We want to be able to use that information, or we want to be able to extend that concept to what we're doing here with functions of multiple variables. So what we want to think about is this idea of an increment. When I say the increment, delta x and delta y, what I'm really saying is some small difference. So if I'm at some fixed point on a surface, if I change the x a little bit and I change the y a little bit, those are my increments. So if I want to find the change in z, so if z is a function of those two variables, similarly, if I looked over here, so I'm going to write something else, I could say that the change in y is approximately the value of the derivative multiplied by the change in x. It's approximately that. So I could say that the function value at y plus, or at some x plus delta x minus the function value at x. So think about the difference between this function value and this function value is approximately the derivative at that point times the increment. And if you'll notice, if you divided both sides by x, that's the definition of, that's the difference quotient, and then using the limit, we actually arrive there. So we want to take that equation, and we want to think about this in terms of multiple dimensions. So I would say that the difference in the z, or the change in z, is the change in both the x and y direction, the function at that value minus the function at the starting point xy. So that this isn't really an approximation, this is just the definition of what those things mean. But if we think about, instead of using just this increment, we think about the differential value, that dx and that dy. What we can do is we can approximate that change by using this differential form. So just like we had this differential form, we can approximate z by using this total differential. So that's dz. So the differential change, so think like infinitesimally small change in z, is the partial of z with respect to x times that differential change in x, partial of z with respect to y times that differential of y. And then we can also write that with those fx notations. But if we use that approximation, that little approximation here, what we find is that we can approximate that change in z by using the partials at the point and then picking values here. Graphically, this is what it means. If I have some value here, and I go some distance in the x direction and some distance in the y direction, well, if I get the new xy change, I find that point on the surface, and the delta z, that change in z, is that much. But instead of computing the function at two different points, I want to be able to approximate. Why do I want to do this? Well, I may not actually know the value of the function at that point. Really good examples of this happen in real world data all the time, where you have information where you've sampled. So you've got instruments and you sample the data at these points, and you want to say, okay, well, what if I go outside the bounds of my sample? How can I approximate what I haven't sampled? And you can use these types of techniques to do this. It happens all the time in industry. And ultimately, what we're going to show is we're going to find these partials, and we're going to choose values. Again, they have to be small values, or the approximations go way, they're not valid anymore. But we can use that, and we're going to do some examples to compare the outputs of the functions to see how close we can get.